Welcome to Happy Homes and Gardens. I'm your host. My name is Daphne Royce. I am a real estate broker, architecture, and interior designer. Levitree is a robotic flood prevention company. Their technology is efficient, long-lasting, and environmental friendly. Lawrence Elwin is co-founder and COO of Levitree. Let's welcome Lawrence to share some insights with us. Hi, Lawrence.
Hi, Daphne. Thanks for having me.
Please tell us who you are and how you and your team became motivated to do flood prevention work.
Sure. Yeah, I'm Lawrence Allen. I'm one of the three co-founders of Levitree. My other co-founders are Trip and Cole. We are all from Santa Fe, which has really severe flood problems and was the motivating factor for starting this company. So Santa Fe has a population of a little over 60,000 people, and they're looking at a flood problem that's $500 to $900 million. They're currently considering a lot of extreme options. Dikes and seawalls are one of the most frequent, but they're looking at really crazy things like big tidal gates like you see on the Mosaic system in Venice. And it's all just to protect the population that struggles so much with sea level rise and subsidence right now. So we were trying to see if we could find a more fundamental solution to these flood problems. And that's really what inspired the team. And because of that, it's been top of mind for us and is really the motivating factor behind Levitree. We've since moved. We're now in Berkeley, so across the bay, where you can see behind me, we're in a 10,000 square foot site, pretty close to the highway, which notably is actually also in a flood zone. So we didn't quite escape that. But this is great because I, was a Berkeley mechanical engineer, and we're also part of Baker Labs, which is a Berkeley incubator program, which has helped us really a lot. We get to pull talent from there. I'm also part of Stanford too, so we pull talent from both schools and really like this central location.
Talk about Santa Fe. What caused the flood?
Yeah, so primarily in Santa Fe, subsidence. So they built a lot of housing on fill, some of it from landfills. And because of that, you get settling over time. And the settling has been really extreme in Santa Fe. There are parts of Santa Fe settling over an inch a year. And because of that and sea level rise, you have a delta now that is changing every year. And in Santa Fe, it's not very good. So a huge portion of the inner part of the city and even the corridor along the highway are now under sea level. And so they use rainwater extraction pumps and try to manage the storm surge, but they're now having problems where even regular tidal events are causing serious issues for the city. And the flooding is just getting worse.
Tell us a little bit about your technology and how would it help a situation like Santa Fe?
Yeah, so Santa Fe is currently looking at a range of solutions, including dikes and seawalls primarily. They're even looking at really large mechanical tidal gates. And what we're proposing is instead to just lift the whole city directly out of its flood zone. So you can do this using underground injection. We are pioneering a new way to do that using biomass. So you're able to do it really inexpensively and on a really large scale. So what we would propose is to lift, both the central area of Santa Fe and also the perimeter that is, directly on the coast. And we would do that in a range of, 3 to 4 feet around the whole city and make it so Santa Fe's problem goes away because the drainage starts working again because, the water will actually flow out of Santa Fe instead of just getting pooled in and needing to be pumped out.
How would you raise it 3-4 feet under so much pressure and with the injection conflict with the underground infrastructures?
Yeah, so the pressures to do these injections are actually surprisingly low. You have an initial fracturing event that's a little higher, but in general, the pressure is about the same as garden hose pressure when you're actually performing the injections. You don't really conflict with underground infrastructure. You certainly do have to consider it during planning, but in general, when you're injecting in an area that's already subsided, you're really fixing that subsidence problem. And so a lot of the infrastructure that's already been strained by that subsidence is actually going back to where it was before when you initially installed it.
I see. How deep do you inject the wood chips and what's in those wood chips?
Yeah, so you're injecting wood chips in a slurry. You need to viscosify it so that you can pump it, and you're just doing water, that viscosifying agent, and wood chips. And when you pump it underground, you're doing that at a depth of anywhere between 15 and 300 feet. I won't go into it, but you get a stress state change at about 300 feet that makes it stop working in most geologies. But that range is really broad, and you use the specific injection depth to determine how far out your injection will spread. So you have a ratio of about 3 to 1 in terms of the diameter that it spreads out to for the depth that you inject it at.
And how long will it last? And do you require any maintenance?
Yeah, so to a first approximation, it lasts pretty much indefinitely, and it requires no maintenance. We sell carbon credits off the fact that it's going to persist for a long time, and we have a lot of evidence for that, some of which comes from the geology world. They dig up 5 million-year-old non-petrified wood, but it also comes from the geotechnical world, where this has been used to lift roadways. You have a lot of lightweight fill that is actually just wood chips. So you have an embankment for the Dumbarton Bridge in the Bay Area that is just on a very large pile of wood chips, basically. And then you have similar on the Alaskan highway system. Washington and Oregon do very similar. So you're building highways on top of wood chip fill frequently, and we get to use that body of evidence to understand that permanence, on a geotechnical level, but also on a carbon sequestration level.
How do robots work in preventing floods and sequestering carbon?
Yeah, so the robots really allow you to do this in a more automated way. We're training contractors, and what we realized is it's just very difficult to run these injections manually, but it's pretty straightforward to do this with a machine learning model. So what we did is we trained a model off of the injections we did at our pilot site, and then used that to run our injections on autopilot. And so the robot is what allows us to do that on the hardware side. So you have a tracked robot that goes around, we call it Wally, and Wally goes around to each injection well and actually performs the injection to the specification that's set in your injection plan, instead of having the contractors have to manage that. So instead, the contractors really just manage the feedstocks on site and the logistics behind that.
How many robots do you need for a project, or do you send multiple robots on site?
Yeah, so it depends how fast you want to do the project. Typically, we would expect multiple robots on site. You have about 3 to 4 days per acre foot per robot. So if you're using a single robot, you can do that acre. That is an interesting measurement, but it's elevating an acre by a foot. So you'll do that in about 3 to 4 days with one robot. But if you wanted to do that faster, you could use two, and you do it in 1.5 to 2 days. So depending on how large your project is, you're gonna kind of size the amount of robots that you need off of that.
Tell us more about underground injection wood slurries, and please describe your technology generally from start to the end.
Sure, yeah. So when you're injecting a slurry underground, you're using a pump to do that primarily. And so you need, moderate pressures are required, and you also need to pass large particles. So your pump gets tuned around those things. And on the other side, you have to make this slurry to begin with. So you have to have an additive that can viscosify it, and you have to mix all of that up with wood chips and water and get that underground. And so that whole process we have mostly automated at this point. And the end net result is that you're applying hydraulic pressure pretty similar to what you would use in a hydraulic jack. You're using a little amount of hydraulic pressure to open a really large space, and so that becomes enough to fracture the soil. It's like a pressure force area calculation, basically. And when you get that fracture, you can kind of start slowly filling the aperture that it creates. And what happens is you get an uplift event from that injection. And so we use that uplift for the flood prevention service that we provide. And we use an array of injection wells to get the perfect uplift and make it even and easy to track.
Do you do any inspection before so you can understand what is underground look like?
Yeah, so we have software actually that does a lot of that for us. So we use our software to understand what's happening underground. You are using a data set of geocores that we've assembled and basically training a model off of that to understand underground geology and be able to do a lot of the upfront planning work before you actually go on site and have to do any geotechnical work. We still usually expect that you will choose to take soil cores on site, but a lot of that can be pushed off until later planning stages because of that software suite.
Can your technology work on sandy soil, marshland, or even with a bedrock underneath it?
It's a great question. So in general, we can do most geologies. There are cost differences between them. So sandier soils, like you mentioned, those have a higher what's called hydraulic conductivity, which is basically a measurement of how fast water will flow through a soil. And because it's higher, you end up needing slightly higher injection pressures and slightly more additive, which adds cost to our injections. You theoretically can inject in bedrock, though we've never tried it and don't anticipate doing that in the near term. You can fracture bedrock for sure, but the soil mechanics become a lot more complicated, and the drilling cost is also very high for that. So we target easier soils. So fine clays are nice. They have really fine grains and make it very straightforward to inject in. It's kind of more similar to just blowing up a balloon or something than it is if you have high hydraulic conductivity.
So who will most benefit from your technology? Can you help with the sea level rise?
Yeah, so everyone should benefit from this technology, which is why it's so nice. You have kind of a new fundamental way to approach flooding problems. Bay areas, cities have huge flood problems, and we hope to help all the people impacted by that. You also have a lot of other interesting verticals. We can do new home developments. We can do wetland mitigation, banking. We can do interesting projects like electrical substations and aqueducts and runways, which are all infrastructure that are typically very difficult to fix when they subside. And you usually have to shut them down, just like you would a highway as well. We get lots of interest from departments of transportation around highways and roadways. Caltrans has 3,000 lane miles at risk right now in California. So we'd love to help with that problem. Long term, we're really excited about really large scale elevations like whole cities and maybe even island creation. So the promise of this technology is really huge, and the verticals are extreme. So we're making this business in a box that we can go license to contractors so that all these projects can get done immediately instead of us going in and trying to jump into every corner of the world and every specific vertical.
Interesting. Can Levitree help stabilize the ground to prevent soil liquefaction?
Yeah, so we don't claim this outwardly, and a lot of this testing is still being done right now by an engineering firm that we're working with. But initial data seems to show that this is better than soil in terms of its stability. So we are hopeful that this might be able to help with liquefaction, but we don't want to make any official statements about that until we get our cone testing back and also some more of the soil mechanics from some of the triaxial loading testing we're doing right now.
Would they come with any negative impact years after injections?
So, you have the surface of the earth supported by the pore pressure right after injection, but very quickly it goes and compacts the wood chips, and you're turning it into pretty much particle board underground. And so when you're thinking about how this is going to act and react to seismic events, or even day to day, you should really be thinking of this as, I have a layer of particle board underground. How is that going to react? Because particle board gets put under maybe 600 psi once. This is under a range of 30 to 200 psi pretty much forever. And so you end up with pretty great soil geomechanical properties.
You mentioned about raising the whole city. How long does it normally take to complete a site for injection? And how long will it take you to finish the entire city?
Yeah, I'm excited to jump into cities. You're going to need a lot of robots to do it. We still have that same requirement, which is one robot can do an acre foot in about 3 to 4 days. So if you're doing a whole city and you want to do it very quickly, you're going to need a lot of robots. But the exciting thing is that you have the option to do it slowly. So instead of these projects being giant upfront capital expenses driven by speculation about sea level rise and about subsidence, we can make this a predictable maintenance expense where you're not planning out to 2100. You're just doing the elevation you need this year to keep up with sea level rise. And we think a lot of cities will choose that. We've already heard from a lot of infrastructure projects that is a really good way to work with them. Caltrans has a massive budget for maintenance, but they need Gavin Newsom's signature if they're going to do some giant, Highway 37 multi-billion-dollar causeway fix on the highway. So this technique, I think, will be used mostly as maintenance injections for whole cities. You might have some initial upfront lift of 1 to 3 feet, and then do an inch or two a year.
Is the Levitree affordable for California?
Yeah, so we're starting with a lot of private projects, and the really great part is it's dramatically cheaper than other alternatives. So it's about a tenth the cost of dikes and seawalls, which is huge, and that mostly works on a city scale. But it's also frequently cheaper than even importing fill. So you only use about an eighth the truck traffic when you use our technology versus fill dirt, because wood chips are so much less dense. And this really helps in California with your CEQA report, for example, and also not having any surface disturbance from these injections, because you're just lifting the whole property as it currently is really huge. And so you end up frequently being price parity or sometimes better, and then having those additional benefits makes it so most projects will end up leaning our direction in terms of general costs and project difficulty.
You mentioned earlier you had to mix the wood slurries before you inject underground, but do you need to take a lot of space to do that?
No, so we typically will have kind of a shipping container in the parking lot and that does that, and then you'll have your rover that goes around and actually does the injections. So we try to keep it really hardware light, using a lot of off-the-shelf parts, working with partners so that we don't have to build it all ourselves, and trying to use things that contractors already have as well, which is important. So you have a system that works cohesively because it's got this sensor and controls hardware, but you also get to leverage all of the existing infrastructure that's in place for these projects and have a pretty simple and general slurry mixing system.
When you inject underground, would they cause cracks split on the structures?
No, so you're doing it really deep. I think it's sometimes lost on people how deep we're really talking about. I would say our average injections are going to be between about 60 and 100 feet. And at that depth, you have, let's say even 60 feet of undisturbed soil. Now, this is a stiff, large column, and you're lifting the whole thing. And so you're not getting a really large amount of deflection. You have the same thing for the underground infrastructure, but you're choosing to do really even lifts with arrays of injection wells that are controlled at a much better precision than you need to prevent cracks in infrastructure. So we use an array of sensors to make sure of that, but it ends up being pretty straightforward to control these injections at the level required to do that perfect lift that you're looking for without any risk to your infrastructure.
How do you monitoring the surface level?
Yeah, so some of that's proprietary, but we use an array of sensors. The sensors need to both feed in really high precision data for your final numbers, but also give a really rich data set during the injection process so that you can use that to do the feedback during your injection to control the direction it goes and a number of other things like the slurry composition and the injection rate. So some of your elevation sensors are feeding back data very quickly and less precise, but the mix of the two allows you to, really accurately control these injections and hit that final elevation number very precisely as well.
Very interesting. Can you describe underground degradations and emission after injection?
Yeah, so this is something that we monitor very closely for the carbon markets. They have a procedure in place. They call it MRV, which is measurement, reporting, and verification. And through those procedures with the carbon markets, we track the CO2 or methane that could be emitted. Frequently, we get non-detect results because it is really hard to degrade wood when it's anaerobic, which means without oxygen. So you have wood, which is made of cellulose, hemicellulose, and lignin. And lignin is really tough and really difficult for microbes to get. And so when you put it really deep underground and you put it under an extreme compaction force, it's really tricky to get anything in to eat it. So you end up having this really long permanence that comes from the really specific storage conditions that you have underground. So that includes the anaerobic part, which is probably the most important, but also a range of other things, including recalcitrants that end up with the net permanence being extremely high.
There are no emissions that will harm the environment at all.
No, there's a number of other factors too that make it so you will have, very close to actually zero. One of them is that you have an oxidation rate through the soil. So you have some flux of, potential greenhouse gases coming up, but because you have such a large distance that they're going through and it's such a small rate, it ends up getting eaten by things on the way up if it were to be created. So we still do a lot of measurement to be sure and to be able to hand this off with a golden stamp to people buying carbon credits. But in general, it is mostly a non-issue for us.
Are you only working in California, or will you also work the rest of the country or even overseas?
Yeah, currently we're only working in California, but we get a lot of interest from Cambodia, as you know, and also Indonesia and Brazil. So we're hoping to hit international markets pretty soon. Post Series A, very likely that we will do that expansion all at once.
How much land around the San Francisco Bay Area are in the flood zone? Do you know this?
Yeah, it's honestly most of the bay. So if you look at a map, a very large percentage of the entire perimeter of the Bay Area was built on fill. And because of that, a lot of it has subsided. And so most cities are not immune from flood problems. It's pretty rare that you'd find a city that doesn't think of that as top of mind. So we're, connected to city councilmen all over San Jose, San Leandro, Richmond, Santa Fe. And it's just because they all have these really terrible flood problems. So it's such a widespread issue that the cities have now joined together in a coalition, also working with BCDC to try to address this at a whole Bay Area level instead of trying to do it city by city like they've been historically. So they now have some much larger plans that they're trying to make work that will protect the cities as a group instead of singularly. This is important because when you have dike and seawall solutions, a lot of times those end up making it worse for the other guy. So they saw this in New York when they were trying to do this giant dike and levee system. And what they found is, anyone that gets left out of that levee ends up flooding worse because of the levee. So part of the reason that Levitree's solution is so great is because you get to manage those a little more granularly and don't have the same problem where people are just getting left out of a solution and then have dramatically worse flooding because of it.
What's in the landfill and how long can they normally last?
Yeah, so I'm not a world leading expert on landfills, but generally speaking, this is just a normal landfill that you would throw your trash in that ended up getting covered with a lot of fill dirt, compacted, and then they built homes on it. And because of that, you have all that trash and that new fill that does end up compressing and subsiding over time. And so that settling can be very extreme and can end with you having a much worse flood problem than you would otherwise have if it was just sea level rise. In the Bay Area, this is mostly the problem, but you have other areas like, for example, the Central Valley that have subsided as much as 20 feet from just groundwater extraction. Long Beach is another example, but they subsided mostly from petroleum extraction. And Mexico City is perhaps the most famous one because it has subsided over 100 feet from its groundwater extraction. So you have a lot of different things that cause this subsidence, and its impact is really subsidence plus sea level rise, which ends up becoming really the dangerous duo that is causing really severe flood problems and making these effects much more pronounced than they would otherwise be.
Where is your website and how can people find you?
Yeah, our website is levitree.com. That's Levitree.com.
Thank you so much, Lawrence. That was a very informative
Thank you too.
interview.
This was really fun, Daphne. Thank you for having me. We'd love to do more flood prevention projects. If you have a project that could use our services, give us a call. Thank you again.
Thank you.